We're a bit new to WebEx meetings, which normally use Zoom. Okay, can you see my screen now?
Yes, sir.
Yeah.
Very good.
Yeah.
Very good. So I will maybe wait for a minute or so and we can get started.
No, some people are ready.
Good morning to all esteemed professors, scientists, and participants present here. It's my pleasure to welcome you all to the 23rd Technical Talk Series titled TransTech Talk Series, organized by KSCSTE National Transportation Planning and Research Center, NATPAC. Through this technical talk series, we aim to provide a platform for experts in the field of transportation engineering to share their knowledge and expertise with us. These talks will offer insights into the latest developments, emerging trends, and cutting-edge technologies in transportation engineering. I would express my gratitude to all of you for joining us today. We have an exceptional speaker with us, Professor Dr. Phanikumar Mantha, who will be sharing his valuable insights on the topic Coastal Water Quality and Public Health in the North American Great Lakes, the science, technology, and policy behind beach management. Before we begin, I would like to invite Sri Sharan MS, scientist at NATPAC, to deliver the welcome address. Over to you, sir.
Thank you, Jida. I think I am audible.
Yes.
Good morning, everyone. It gives me a great pleasure to welcome you all to this session organized by KCSTE National Transportation Planning and Research Center. Established in 1976 by the Government of Kerala, NATPAC was created to address the traffic and transportation challenges of our state. Since its amalgamation with the Kerala State Council for Science, Technology and Environment in November 2002, the center has been operating under the Department of Science and Technology with a vision to integrate research and development activities across Kerala. NATPAC is a multidisciplinary institution renowned for its expertise in traffic engineering, transport planning, highway and pavement engineering, public transport systems, geotechnical engineering, road safety, water transportation, geomatics, and transport economics and management. With regional offices in Kozhikode and Ernakulam, the center's scientific and technical personnel are organized into 5 dedicated scientific divisions, ensuring specialized focus across various domains. Guided by the 2 key bodies, the Research Council for Technical Matters and the Management Committee for Administrative Functions, NATPAC benefits from the leadership of the distinguished professionals. The Research Council, chaired by Professor Tom V. Matthew from the Civil Engineering Department at IIT Bombay, includes esteemed members such as Dr. S. Velmurugan, CSIR CRRI, Professor Lalita Devi Vanajakshi, IIT Madras, Professor Kusum Sundar Reddy, IIT Kharagpur, Professor Ashalata R, College of Engineering Trivandrum, and Professor MVLR Anjaneyulu, NIT Calicut. In our ongoing efforts to disseminate knowledge, NATPAC organizes the TransTech Talk Series, a monthly online technical initiative designed to benefit students, researchers, and stakeholders. Our inaugural lecture, titled Advancing Crash Frequency Prediction Modeling Using GIS, was delivered by Dr. Srinivas S. Pulugurta, followed by engaging sessions on challenges and solutions in cold asphalt pavement recycling by Dr. Rajiv B. Malik. To date, we have successfully conducted 22 lectures covering diverse fields within traffic and transportation. Today, we are proud to present the 23rd talk in the distinguished series. For this session, we are honored to welcome Dr. Phanikumar Mantha, Professor in Department of Civil and Environmental Engineering at Michigan State University, East Lansing, USA. Dr. Phanikumar brings an extensive expertise and experience to the session, and we look forward to an engaging and enriching discussion. After the talk, we will have a Q&A session where participants are encouraged to raise their questions either by unmuting themselves or posting their queries in the chat box. On behalf of NATPAC, I extend a warm welcome to everyone present here today. Let us look forward for an informative and interactive session. Thank you.
Next, I would like to invite Srimati Veena KS, scientist at NATPAC, to introduce our esteemed speaker.
Good morning, sir. Dr. Phanikumar Mantha is a professor in the Department of Civil and Environmental Engineering and Ag Bioresearch at Michigan State University in East Lansing, USA. Dr. Mantha earned his PhD from the Indian Institute of Science, Bangalore in 1990 and worked as a scientist at the CSIR Center for Mathematical Modeling and Computer Simulation, National Aerospace Laboratories in Bangalore between 1990 to 95, where he received the Sir C.V. Raman Young Scientist Award. Research interest in his group include hydrology, water resources, coastal, nearshore process modeling, and biophysical modeling. Dr. Mantha published 80+ papers in peer-reviewed international journals and presented his work in numerous national and international conferences. He is a fellow of the Geological Society of America and is currently a US Fulbright Scholar visiting India. His research was funded by federal and state agencies, including the National Science Foundation, National Atmospheric and Oceanic Administration, National Aeronautics and Space Administration, US Department of Agriculture, and United States Geological Survey.
Now, I would like to invite Professor Dr. Phanikumar Mantha to deliver his talk. Over to you, sir.
Thank you so much for those nice words and the introduction. I'm assuming all of you can hear me all right. If you see any issues with either audio or video quality, please let me know. From my end of the screen, I cannot see anyone other than my own screen. So it also looks like I cannot read the chat. So feel free to raise your voice if there are any questions. I'd like to make this a fairly informal talk. So questions are welcome. Feel free to stop me at any point. So with that, let me go ahead and step into the talk. So as you see from the screen, the topic is coastal water quality with implications for public health in the context of North American Great Lakes. But the research that I present today is applicable not just to the North American Great Lakes, but to any coastal region in the world. And I believe this is particularly relevant to Kerala because of the extensive coastal environment there. And I was also visiting Kerala. I was there recently. So my special thanks today for this invitation to Dr. Sabita, and also my Fulbright host, Professor Santosh Thampi, in the Civil Engineering Department at NIT Calicut, whose invitation helped shape some of the ongoing research that we are doing, including the National Institute of Technology and the US India Educational Foundation and the Fulbright program that allowed me to visit India this past fall. And also I'd like to acknowledge a lot of my students and former colleagues and current colleagues with whom I have been fortunate to work with. And a lot of the research that I'm talking about today is collaborative research that I was able to do with all of these great researchers. So let us talk a little bit about coastal water quality and why it is important. Good water quality, we all know, is extremely important, especially from the point of tourism. If water quality is bad, that directly negatively impacts tourism, coastal tourism. In the context of United States, for example, beaches really generate a lot of income for the local governments, and you do not want to close a beach unnecessarily. But on certain days, beaches have to be closed because they are not safe for the public. So that is the first context from a tourism point of view, coastal tourism. beach resorts, boating, and all types of recreational activities, they're all heavily dependent on clean water. Polluted water negatively impacts tourism. The other important aspect, which is probably fairly easy to see, is that fisheries and aquaculture depend on good water quality. So, for example, we're all aware of bacteria like Vibrio, for example, that infects fish and shellfish and contaminates the seafood. So, having good water quality is important for fisheries and aquaculture. And the long-term sustainability and resilience of coastal areas depends on good water quality. So the question becomes, how do we ensure good water quality? And when water quality gets degraded, or water is contaminated, how can we detect that sufficiently ahead of time so that we can take some interventions and address the situation? So that is the main context of my talk today. But coastal water quality, as you know, is a very general term. So we can talk about so many different things under coastal water quality. For example, you can talk about nutrients. You can talk about plastic pollution. You can talk about all types of chemical contaminants. And you can also talk about many different types of microbiological contamination. So nutrient pollution, if you want to reduce that, we have to limit agricultural runoff, because we know that nitrogen and phosphorus, elevated levels of those nutrients, cause eutrophication, and we get into issues like harmful algal blooms. And plastic pollution is a big issue. There are negative health effects. Environment is impacted, especially single-use plastics, and there is a lot of emphasis worldwide on plastic pollution because we're just beginning to understand how much negative impact plastic pollution has. So that is also an important issue under the broad umbrella of coastal water quality. Chemical contaminants, there are any number of chemical contaminants that we can think of. And of course, microbiological contamination, as I mentioned, is important from a human health point of view. So today I'm going to focus mainly on the last category, microbiological contamination, and there is a reason for it. If you think about chemical contaminants, the negative effects of chemical contaminants, they really take place over a long period of time. Exposure, if we're drinking, for example, water that is contaminated with chemicals, over a long period of time, you begin to see issues like cancers and other types of health outcomes. But microbiological contamination, on the other hand, directly impacts you. So if you get exposed to poor water quality, you will see the effects of it within a few hours to a few days. So from a management point of view, therefore, microbiological contamination is extremely important. And in the US, it is this microbial contamination that is monitored regularly, so that beaches are closed to the public whenever the microbial contamination exceeds a certain threshold. For example, the bacteria concentrations, when they exceed a certain threshold, people decide to close beaches to the public. So that is the context that I'm talking about for this talk. Then the science behind this context becomes, how do we know what the concentrations of this bacteria are? And that gets you into technology, because we will talk about measuring, bringing a sample of water to the lab and testing it, or developing mathematical models to make predictions, and all of that is the technology. So we will talk about that. So in the Great Lakes, I'm now switching the gear here. We're getting into the North American Great Lakes. There are any number of beautiful beaches in the Great Lakes, but something to keep in mind is what looks really beautiful can still be contaminated. That is the important thing to note here, because we cannot tell with the naked eye by just looking at the water that it is clean. That sometimes, you know, water can be deceptively clean. It can still harbor contamination. So that's the point I'm trying to make here. Water quality cannot always be judged by the naked eye. Water can look good and it can still cause illness when people are exposed to it. For example, when people go swimming or some water gets into their system by ingestion. In the US, local governments are responsible for testing that water regularly and informing the public. And typically signs are posted at beaches. And if water quality is bad, then there is a red sign similar to the traffic sign that says stop. You cannot go and swim at this beach. So that's, but how to arrive at that decision in a timely manner, that is the most important science objective, science or technology objective. So a little bit of background here. Now, when you talk about microbiological contamination, there are hundreds of different bacteria and viruses that can all make us sick, from types of diseases like gastrointestinal diseases to respiratory diseases. Any number of possible health outcomes, negative health outcomes are possible. With so many bacteria and viruses that one can test for, how will you decide which one to select for making a determination that today the water quality is bad? That is the basic, assumption here in public health. Typically, because it is impractical to measure each and every one of these microorganisms, we select what is referred to as a fecal indicator organism or a fecal indicator bacteria, FIB or FIO, depending on which one we use. And that indicator organism is typically one single organism, such as E. coli, which is very well known. In freshwater systems, typically E. coli is used as that surrogate or that indicator bacteria to make that determination that water quality is either good or bad. In marine systems, this would be more relevant to Kerala, for example. Instead of using E. coli, people typically use the Enterococcus bacteria as an indicator. So then the question becomes, if the concentration of either E. coli or Enterococci is high, typically above a number like 300 colony forming units or CFU per 100 ml, when that threshold exceeds, we determine that the water is not safe for the public and we close the beach. So that is the basic idea here. Excuse me. So the fecal indicator organism idea is that that specific microorganism is used as a surrogate, and then these organisms signal the presence of harmful pathogens. So that's the basic idea here, and I want you to focus on this basic assumption because sometimes that assumption is not satisfied. So the assumption we are making here is that if E. coli concentrations are high, then we are assuming that the viruses, because it's usually the viruses that make us sick, those viruses and other pathogens are also high. Then now that assumption is not always correct. There are instances when E. coli concentrations are high because they're probably coming from a different source, naturally occurring sources such as soil, and there may not be any viruses or other pathogens that cause illness. In those cases, you close the beach, but you are unnecessarily closing the beach. So there are situations like that we should be aware of, but by and large, this model of using the idea of a FIO or fecal indicator organism has worked very well. All of the beaches in the US and in Europe and UK, for example, they still use this model. And this has become a successful model for public health in these countries. So that is what I will talk about. So the motivation, as I said, the photograph that you see here is the beautiful Varkala beach. I took this photo, I think last month in November or October when I visited last. So a lot of the people are at the beach on a beautiful bright day, and some of them are getting into water. So the last thing on their minds is getting sick from exposure to contaminated water. This is, of course, a beautiful beach. I don't think there is any contamination nearby, but you never know. So the motivation for this type of research is human health, obviously. We also want to make sure that the local economies are thriving. They are thriving and not getting negatively impacted by bad water quality. And the sustainability of coastal ecosystems is also something of interest, because beach water quality is one indicator of the overall health of these ecosystems. So if we want to make sure that the local economies are thriving and the ecosystems are sustainable, we want to make sure that the water quality is good. So now one issue that I want to let you know is that the current management methods in the US are slow because they use laboratory methods. In other words, what they do is they bring a water sample from the beach, they have to run a test, and that test will take anywhere from 24 hours to 48 hours, which is 1 to 2 days before the result comes out. That is not a very good way of managing these beaches, because effectively then, if you are doing that, what you are saying is, well, you went to that beach and you swam there yesterday. Probably you shouldn't have done that. That's no way to manage a beach, because you are effectively, your decision to keep the beach closed or open is behind by 1 or 2 days. So it's really not a good way to manage. So that is where models become very attractive, because what we can do, we can develop mathematical models based on the data that we collect at our coastal areas. And then once the mathematical model is tested, we can run the models significantly fast compared to the time it takes to actually run these samples in the lab, these assays in the lab. And there is no delay of 2 days. We can actually run these models very quickly. So that is what I'm going to talk about today. How can mathematical models that are well tested based on field observations be used to generate these forecasts in a timely manner, so that we can close or open these beaches and protect the public from getting exposed. So that's the topic of my talk today. And there is also something I want to point out. This is not just related to freshwater beaches. This research is equally applicable, as I said earlier, to marine areas, as in Kerala, for example, or on other parts of coastal areas in India. And because the fundamental processes controlling transport of these pathogens is the same, whether you're talking about freshwater or marine water. And there are a lot of similarities in the way these microorganisms get transported, and microorganisms also get their concentrations go down. A natural process called die-off, sometimes we use the term inactivation. Think of this as simply bacteria getting killed. Sunlight kills bacteria. So sunlight is one of the most potent manners in which the bacteria concentration goes down, and that is due to direct DNA damage of these bacteria. In addition to sunlight, there are other factors. One of them is salt water, for example. Salinity in marine waters kills these bacteria. In addition to that, there are other processes. For example, there can be grazing. Other microorganisms in the water can graze upon these bacteria that we're looking at. So these are all processes by which concentration goes down. And we have to include all of these processes in our mathematical models, in addition to the hydrodynamic modeling, which is the most important model that we have to develop. So as I mentioned, the timeliness of beach water testing is extremely important. Current methods take anywhere from 24 to 36, sometimes 48 hours before you get the results. And during that time, the water quality at beaches can change dramatically. In fact, water quality can change within a few hours. So that's the mismatch in timescales that I'm talking about between the time it takes to actually get the result out from your sample that you collected versus the actual conditions in the field. They can change dramatically. There are a few rapid methods that are becoming popular. For example, the qPCR method, quantitative polymerase chain reaction. It's a rapid method, but it still takes time. It's not as fast compared to the models. So predictive modeling, as I said, is extremely attractive here. So these are just some signs that you see at US beaches. For example, on a day when the water quality is good, you see the sign on the left that says water quality is good. Otherwise, you see the sign on the right, which is the red one that says the beach is closed. Now, typically in some states, for example, the Great Lakes states, we use this number. The E. coli concentration, if it is greater than 235 units, then that means the water quality is bad. You have to close the beach. So there are a number of interesting science questions here. There are a lot of technology-related questions. There are policy-related questions here. Science questions are, we can ask any number of questions. For example, what are the factors that influence the fate and transport of these bacteria and viruses that make people sick? That's the most fundamental question that we can ask. The second question, if you're developing a model, is what are the typical inactivation or die-off rates of these bacteria in freshwater systems and in marine systems? In fact, it turns out there's only one term that is needed in addition to the freshwater formulation that will for the model to work in a marine setting, and that is salinity. So there is salinity, there is solar radiation, shortwave radiation that kills the bacteria, and there are other processes like grazing, and bacteria also settle to the bottom of the lake or to the bottom of the sea, and that is another important process. And then there are other questions we can ask, interesting science questions. Technology-related questions are, what are the key characteristics of a successful model? How can we develop a good model that is faithful and that gives us good information about E. coli or enterococci bacteria? And then there are policy questions, how to manage beaches effectively and how to protect the public from getting exposed to this. What types of behavior are conducive to good health outcomes, and what types of behavior, by that I mean, is it, are people who swim in the water, who get their head underwater, are they getting sick more often than people who just float on the surface and don't get their head into the water? You know, these are behavioral questions that will try to understand what types of human behavior get people more sick. So there are all of those questions. Our research has all of the components. We have done field research, we have done lab-based research, we have developed mathematical models and tested them. And this is where collaborative research becomes extremely important, because no single individual researcher can be an expert in all of these areas, especially when you talk about microbiology, hydrology, hydrodynamics. This is a truly collaborative research, and it's important to be able to work with colleagues across different areas. So these are some of the processes that are important in a coastal area. You have temperature fluctuations, you have sunlight bringing the UV radiation into the water column, and you have birds that actually contribute bacteria to the coastal area, and you have runoff from rain in an upstream area that is washing to the coastal area, bringing with it additional bacteria, and these bacteria can attach to suspended sediment, and the bacteria can settle out of the water column. But on those days when the wind is high, some of these bacteria can again get resuspended back into the water column, and these are all important processes if you want to be able to predict their concentrations. So as I said earlier, the decay or loss of bacteria, in addition to transport, such as advection and dispersion, the decay or loss is due to sunlight. Temperature effects are important. As the temperature increases, the losses are also higher. Salinity causes direct DNA damage, as I mentioned. Predation is important. Nutrient deficiency can also negatively impact the growth of bacteria, and there can be toxic substances. And as I said, settling is another important process. So I want to show you some photographs here that show how these plumes, the plume is the term that we use to refer to this shape that you can see here. This is basically the mouth of a river. A river is draining into a lake, and you have exactly the same situation at the beaches in India, in the coastal areas. Some river comes and drains into the coastal ocean. And that river, typically what happens is the river water is a few degrees, has a temperature difference compared to the river, to the lake or the ocean water. And also, because the river is draining the landscape, it has higher suspended sediment concentration, which you can see very clearly here. The dark brown water is all suspended sediment concentration that you can see, and we have taken these pictures from an aircraft so that you can clearly see the plumes. But the important message here is that these plumes change direction. As you can see, on this day, June 19th, the plume is going to the left, and then here it's going to the right. Sometimes it goes straight down. Depending on where you are, let us say people are swimming on this beach here. At this time of the day, all of the people swimming here are getting negatively impacted by this plume because this is directly coming towards them. But the difficult thing here is that you cannot tell by just looking at it with the naked eye. If you are especially in that water, there is no way to tell whether that water is contaminated or not. In other words, we cannot see this gray or black patch of water, which is what we are referring to as the plume. So that plume dynamics is extremely important, and it changes direction from left to right within just a few hours. If it is moving to the left, all of the people swimming at this beach are now impacted, but these people are safe. And if it is moving in the other direction, all of these people are impacted and these folks are safe. So the prediction, the mathematical model should be able to predict that reversal of the plume, in addition to, of course, predicting the concentrations correctly. This is another photograph. And I like this photograph because you can see what is happening here. Do you see the chimney at the background? And you see the smoke going in that direction. That smoke going in that direction tells you that the wind is actually blowing in this direction, which means as the water is trying to come out of this river mouth into the lake, that water is not actually going into the lake, but it's getting pushed against the shoreline such that several kilometers of the shoreline are negatively impacted by this contaminated water. And all of the people swimming here, they're all negatively impacted. So all of the people on that day. So this is typically one of those days where it is not a good idea to go to the beach and swim in the water. So it's being able to predict these types of events. So I will now talk about some of the modeling that we have done, and all of these models are tested because we also do field work and go out and collect data, hydrodynamic data. on currents, waves. We collect suspended sediment data. We also collect bacterial data. I will talk about model complexity is an important concept here because you want to use a model that is sufficiently predictive of the key processes, but there is probably no reason to make it excessively complex because you can make these models very complex. But if a simple model works, that is the probably the best way to do. So I'll talk about two models. Model one includes hydrodynamics, which is advection and dispersion, and of course, the decay of bacteria. But it does not include suspended sediment. It does not include waves, current wave interactions, and it also does not include other processes such as bacteria attaching to suspended sediment and settling out of the water column. So let us see how these models perform. Typically, these models depend on the hydrodynamics first. So we solve the hydrodynamics equations. Hydrodynamics is tightly linked to temperature because, as you know, there is stratification in lakes and coastal ocean. And once you solve those equations, we can solve equations for the concentration of bacteria. Now notice that this equation has a sink term, negative S, where that S accounts for all of the processes that contribute to the loss of bacteria. For example, there is a base mortality term here. Base mortality simply means these bacteria are going to die no matter what. They're not going to live forever. They're going to die at some natural rate, and that is that rate shown here. But if in addition to that natural death rate, which is called the base mortality, these bacteria, the bacterial die-off happens at a faster rate if the sun is there and if sunlight is strong, and typically, you know, midday, for example, sunlight, solar radiation is pretty high, and that solar radiation, which is incident on the ocean or lake surface, decreases exponentially as a function of depth, and that is what is shown here. In addition to that, bacteria settle down out of the water column, and that is shown here. All of these factors increase with temperature. In other words, as the temperature increases, the loss rate associated with all of these processes also goes up. So that is what this equation is telling us. Now, in this equation, FP denotes the fraction of bacteria that are attached to the suspended material. So now there is another model that we can talk about. This is a more complex model, but this model includes suspended sediment transport dynamics. It also describes how bacteria attach to suspended material and how they detach from that suspended material. Erosion, apologies for the typo there. Erosion and deposition are modeled. Wave characteristics are modeled because in the coastal environment, as you know, waves suspend material from the bottom of the lake or the ocean, and that is important. Sometimes on a clear day, there is no contamination coming from the river, and you sometimes see contamination just coming from the bottom of the lake or the sea coming back into the water. So sometimes those processes become important, and this model can actually describe that. So those are all the processes described. And the second model, which is the more complex model that I talked about, takes this attachment of bacteria and settling of that bacteria into account. Notice one thing, bacteria are very small. They cannot settle on their own. In other words, there is always something going on in the water column. There is always turbulence that will prevent bacteria from settling on their own because of their small size. Therefore, the mechanism that is needed for bacteria to settle out of the water column is they have to first attach to something that is much bigger than the size of a typical bacteria, and that is the suspended sediment. Typically, suspended sediment particles are much larger in size. So bacteria attach to those suspended materials, and they settle out of the water column. Excuse me. So we basically use unstructured grid methods. This is typically what a computational mesh looks like. I'm talking about Lake Michigan here in North America. These models describe the shoreline features and all of the important features. And I'm going to now show you some data, the hydrodynamic data, but to give you a little bit of context, these three beaches that I'm talking about, there are three beaches here that you can see, OD1, OD2, and OD3. Those are beaches where we collected data. And there is a river mouth. This is called the Burns Waterway, and that's just a river. So that river plume is coming out, and sometimes it goes this way to the left, sometimes it goes to the right, and depending on which way it goes, the beaches are impacted, and that is what we are trying to model. But before we actually model the E. coli, we have to first describe the hydrodynamics. So we typically collect data in the coastal area. We take a small boat or a ship, depending on what is available, and we deploy these types of instruments in the coastal area. And then these instruments are left there for typically several months, 3 months, 4 months, sometimes up to 6 months. They have enough battery and memory to collect all the data on currents and waves. And this is one comparison between observed currents and simulated or model generated currents. As you can see, there is general agreement. As you can see, these are vertically integrated currents. In other words, instead of comparing at several different heights along the depth of the water column, we integrate the currents, and that gives us the vertically integrated current. It makes a three-dimensional flow field into a two-dimensional flow field, basically. And then that makes it easier to show the comparison. So this is a typical comparison in the year 2008. Excuse me. So here is another comparison, alongshore velocity and cross-shore velocity. Typically, the velocity in the alongshore direction is larger compared to the cross-shore velocity. But again, as you can see, the model is doing a reasonable job. These are some vertical profiles of velocity. And again, you see that the dots are the observed velocities, and the solid lines are the simulated velocities. So again, the model is doing a good job. Now, those are all current comparisons. In the coastal areas, the waves are also very important, especially from the point of sediment transport and erosion and resuspension. Waves play a very important role. So if you only simulate currents, that is not enough. So here is a comparison between our wave model generated outputs and the observations for the significant wave height. There are other similar comparisons that we have done as well, but this is just one typical comparison. And here is a comparison with suspended sediment concentration. So now let us talk a little bit about what is it that we want a model to do? What are some of the key characteristics of a successful model? As I mentioned last time, I showed you those images of river plumes going to the left and going to the right. One of the things our model should do is reproduce that dynamics correctly. If we don't reproduce that dynamics, the plume may be going to the left, whereas in reality, it may be going to the right, then that model is not very useful. So as I said, the model should faithfully describe flow reversals in coastal areas, whether you're talking about a lake or a river or a coastal marine area. There are those flow reversals, and the model should capture those reversals. The model should accurately describe tracer transport over long periods of time. Now, what do I mean by tracer transport? Think about the distribution of salt, for example, or think about any conservative substance. Imagine releasing some dye in the coastal area, like a tracer. A dye faithfully describes the movement of water, but it does not react. That is what we refer to as a conservative tracer. The conservative tracer is the first thing we typically model, because reactive transport, such as the transport and fate of bacteria, include additional processes. But before we go there, we first describe tracer transport. And then the model should describe the E. coli mechanisms, inactivation or loss mechanisms over long periods of time. So typically in the Great Lakes region, the beaches are in high demand over all of the 3 months of summer, because it is nice outside and people try to go to beaches with their families and, especially children. So that is the test of a good model. So here is the comparison that shows those characteristics. As you can see here, on the x-axis is plotted the time when a flow reversal took place that particular year. And then on the y-axis is the flow reversal predicted by our model. As you can see, this nicely fits into a 1:1 line, or a 45-degree line, which shows the match is almost perfect, except these 3 points here. Turns out these 3 points are data coming from an older version of the instrument. That instrument is not as accurate as the more recent instruments. So that's the reason. It's a measurement uncertainty or error that is associated with the measurement. There's nothing wrong with the model. So that aspect is captured well. The second important point is to be able to describe tracer transport in the coastal area. Now, you probably know that conducting a tracer study is a lot of effort, a time-consuming business. Typically people do tracer studies over a period of 1 or 2 days, and even that is very time-consuming, requiring a lot of planning. If you're talking about longer periods of time, like 3 months or 6 months, it's almost impossible to do a tracer study over such a long time. But the idea that we have used here is the idea of naturally occurring tracers. For example, when river water gets drained into coastal areas, there is a signature of the river in the coastal water. And one of the ways we can capture that signature is using probes for conductivity or turbidity. They tell us that the elevated turbidity or elevated conductivity are measures of the signature of riverine water in coastal areas. And here we are using conductivity as a tracer over this long period of time, almost 3 months. And as you can see, the model is describing the observed tracer concentration reasonably well, and that gives us confidence that, okay, this model can describe the next variable of interest, which is the E. coli bacteria. And here is the comparison between observed and simulated E. coli. As you can see, the model is doing a pretty good job. Remember that we are most interested in the peaks, because peaks are bad water quality, right? This is E. coli concentration. And notice that the y-axis is shown on a log scale. That is how typically bacteria and viruses, they're always plotted in a log scale, because these are not like chemical concentrations. These are microbiological variables. We typically plot them on a log scale. And anytime the peak is captured well, that is a good thing. That means the model is doing a good job of capturing those bad water quality points. Those are the days, for example, look at this day, for example. This is a day when beach should be closed because the bacterial concentration is high. So we have also developed a number of statistical models, and we found that statistical models can also describe these concentrations pretty well. And in fact, their predictive ability is quite comparable to the predictive ability of the models that I just described. I tend to call them mechanistic or process-based models. We're solving a lot of partial differential equations, but these statistical models are simple compared to the complexity of those mechanistic models, yet their predictive power is just equally good. The R square is around 0.75, and mechanistic models also have comparable R square. So this is very attractive for managing coastal areas. We can develop statistical models, and these days, in fact, a lot of my colleagues, including in my lab as well, we're working on machine learning approaches. The advantage of machine learning approaches is we can make predictions in a fraction of the time once those are tested. And there are, this is a very exciting time for some of these areas of research with machine learning really helping us make good predictions. So here is a comparison of the statistical and mechanistic models. As you can see, the statistical models are doing either better or at least comparable to the mechanistic models. So this table here again shows a summary of all of those. If you look at all of these samples that we collected over that 3-month period, turns out the statistical models are just as good as the mechanistic models. So that's the important message there. Also, I talked about 2 types of models in the past, if you remember. One is the simpler model without any suspended sediment and other bacteria sediment interactions, and another one with all of those processes. I have not shown you the equations because it runs into several slides and tends to take a lot more time, but I have summarized the comparison here. As you can see, by including those additional processes, the model definitely becomes better. We have higher predictive power if you include all of that. So that complexity is justified for this beach, but it is probably not always justified for all other beaches, depending on what is happening. So you can see the improvements in model performance. For example, the RMSC value, it's a root mean squared error value, and that error has decreased by including those sediment bacteria interactions. Okay, so switching gears a little bit here, as I mentioned earlier, E. coli is an indicator bacteria. Now, in freshwaters, E. coli works well, but in marine waters, for example, in Kerala, E. coli is not the best. The reason is the salinity kills the bacteria, and it tends to not give you the right idea about contamination, because those bacteria are not surviving very well. On the other hand, enterococci bacteria are a better indicator for marine waters. There are other types of indicator organisms that a lot of people are interested in these days, and those are what are called bacteriophages. A bacteriophage is a virus that selectively infects bacteria. For example, if you take the E. coli that I just talked about, there are a group of bacteriophages that selectively infect the E. coli bacterium, and those are called coliphages. Coliphages are basically viruses. And the reason why coliphages, there is a lot of interest recently, EPA scientists and a lot of other colleagues are looking at coliphages because they are very similar in behavior and size and everything else to the actual viruses that actually make people sick in coastal waters. So we have this paper come out with one of our grad students, both Amar and Chelsea are grad students in my lab, and Chuan as well, where we looked at this question of, can we model the transport of these viruses, these coliphages, in natural waters? So we answered that question by applying the same models we developed earlier for E. coli bacterium. And of course, the rates are different, some of the processes are different, but the important message here is that we are able to, this model is able to predict the fate and transport of viruses very well. And this is good news because this works very well in marine environments. And also these are more similar to the viruses in their behavior. So that's the interest. So the search for the best indicator goes on because that's an active area of research. There is no indicator that is perfect from all points of view, but this is taking us one step closer to that better indicator organism. Now the next question becomes, the models are good, but how do we actually manage these beaches? Are we going to run these models every day, and who is going to inform the public? This is what I was referring to earlier as a technology question, where the technology actually impacts the public health outcomes. So we have deployed these water quality sensors where a number of variables like turbidity, conductivity are measured. And then there is also a weather station near these beaches. And then there is cellular telemetry where this data is uploaded to the web. And then we run these programs automatically on our computers. They download this data and they run our statistical models. Remember, the statistical models that I talked about are doing a good job. They're doing just as good as the mechanistic models. And those outputs of whether a beach should be open or closed are sent by RSS feed by 9:30 in the morning to the beach managers. And lifeguards get this data on their smartphones or laptops. They know early in the morning whether a beach should be kept open or closed to the public. So this is one example of one successful example of how models can be used to actually inform people and protect people from getting exposed to contaminated water real time. So that is an important development. Now, the same models can be used in many different contexts. For example, coastal, as I mentioned earlier, coastal water quality is a very general term. You can have harmful algal blooms generating toxins, and we can do exactly similar model development for those scenarios as well, although those models they will be slightly different because the processes we're looking at will be different, but the same framework can be applied, and then we can make real-time predictions of water quality to make decisions. So this is a policy-related question, how to manage beaches more effectively. Combining these mechanistic models with machine learning approaches is a very exciting possibility, and this technology already exists today. So to kind of summarize my talk for today, mechanistic models are useful tools and they have a great potential, but require considerable computing power. The simpler statistical models and machine learning approaches are very attractive these days. And also sensors are relatively inexpensive these days compared to 10 or 20 years ago. Sensors used to be very expensive. These days, you can measure nutrient concentrations, conductivity, turbidity. So many water quality variables can be measured with relative ease, and these sensors are not very expensive. So once we deploy these buoys, water quality buoys, that data can feed these mechanistic or machine learning models, and we can begin to make decisions to manage coastal areas and protect people. And also, this is an important component of how to improve the local economies as well. So with that, I will conclude my talk. And here is to just give you a sense of what this looks like. This is generated by our numerical simulation. I'm not sure if you're able to see this or not. If not, I will try to play it separately. But that is pretty much the end of my talk, and I'll be happy to answer any questions.
Thank you, sir, for this elaborate presentation.
Thank you so much.
And actually, before going to the questions, actually, we have Dr. K.V. Jayakumar, former Research Council member of NATPAC and former director CWRDM. He's working with IIT Dharwad currently. Hello, sir. Sir Jayakumar, sir. Hello. Jayakumar, sir. Okay, he's not connecting. Maybe. Okay, now we can take questions. Anybody having any questions can please unmute yourself and ask the question, or else you can post it in the chat box. Hello. Samson, sir. Sir, actually, I have a question.
Yeah, sure.
What will be the time gap between the data collection and the time required to give a warning to the public? How much time it will take?
That is typically, a day to 2 days using the traditional culture-based methods, because these samples are brought to the laboratory, and they use this agar plate where the nutrient is there for the bacteria to grow. And once the bacteria grow, you look at the plate and count the colonies, and that takes up to 1 or 2 days. The rapid methods also take several hours, so there is still delay. So that is where the models become very attractive for managing these coastal waters.
Thank you,
Professor
sir.
Phanikumar, Professor Jayakumar here.
Hello, Professor Jayakumar.
Yeah. There is a conference going to be held 2 years from now on coastal reservoirs.
Oh, okay.
Basically, it is a reservoir which is planned called, I don't know, heard about Kalpasar.
Yeah.
It is that, yeah. So there is a conference being held in the year 2026 at Goa and IIT Dharwad.
Oh, I see. Okay.
And a lot of your works are relevant to that particular course.
Thank you. Yeah.
And I really enjoyed, your presentation there.
Thank you.
And some of them are very relevant. Visakhapatnam coast, which I had done some work.
Yes.
And also the coastal Kerala. A lot of very interesting. Thanks for sharing.
Yeah. Thank you. One of the exciting things about this area is now the sensors have become significantly better compared to 10 or 20 years ago, which means we can really make all these decisions of how the water quality is changing in very close to real time. So that's the exciting part of this technology.
Yeah.
Thank you. Yeah. I believe there was a question in the chat. Let us see.
Yes, sir. Dr. Remisha TV is asking, she's telling that thank you, sir, for a very informative presentation. How significantly do wave height and wave period variations impact the dispersion and persistence of E. coli in coastal areas?
Oh yeah, that is a wonderful question. Thank you. Yeah. It turns out at the beach sites where we collected all of this extensive field data, we found out that upwards of 20% of the time, waves affect the bacteria. In other words, if you are using a model that did not have wave processes and wave dispersion, so erosion, settling, you are basically under predicting the E. coli concentrations about 20% of the time. The rest of the time, your other model without the waves will still work. But here is the difficult part. On any given day, you cannot predict exactly what kind of wave height you're going to get. So, from that perspective, it is always safer to use a model that has all of the complexity that is needed to describe these processes. But to answer your question, roughly upwards of 20% of the time. But that this is specific to those beaches. In other words, if you go to another coastal area, those numbers can be very different.
Good morning, sir. This is Sanjay from NATPAC.
Hello, Sanjay.
The thing is actually how the local governments are actually able to implement this particular thing, especially because it may definitely affect the local economy also.
Yes.
So
yes.
how we be?
That's a wonderful question. This is where local governments, first of all, in the U.S., the U.S. EPA, the Environmental Protection Agency, mandates that every state government should have these monitoring programs in place. Okay, that is the federal mandate. Now, states basically what they do, they distribute this authority to the counties. So it's basically going one step down in terms of local governance. Now, every county in the state has a health department. They are responsible for a few beaches. So they're responsible for going out, collecting the samples, and then collecting all of this data, developing these statistical models. So each state government is responsible for doing that. And then they have their own manpower. They have beach guards at beaches. They have beach managers who make these decisions. So this is coming from the federal level to the state level to ultimately to the county health department. And it is that county health department which is responsible for making this happen at their county level, which only involves a few beaches. But actually, your question is an excellent question, because in my opinion, the correct way to do this is to not look at counties or these political boundaries, because natural processes do not care about whether it belongs to this county or that county. Whether if you are talking about coastal water knows no boundaries. There are no political boundaries. So the correct way to do this is to not worry about this county or that county, but to actually do it just like we run a weather prediction model, right? Weather prediction models don't look at counties. They just make a prediction. That is the correct way to do it. Also in the process, the reason why I say that is we save money, because imagine each county, they are doing the same thing that the next county is doing. If they pool all the resources, they can actually come up with better models, better technology for monitoring their coastal, air resources. And that is the way to do it, in my opinion. In fact, we are just working on a paper that talks about that model, how you should really manage beaches. And of course, that becomes a policy question. It goes beyond the science and technology. So, but that's a good question.
Yeah. Thank you, sir.
Thank you. Yeah.
Hello.
Yes, Sarita.
Actually, Dr. Santosh Thambi, Professor NIT Calicut is here. Sir, do you have any comment?
Sir, so nice seeing you here. I don't have to ask the question, because, as you know, we have been talking about this
Yes.
over during your stay here.
Yes.
So, because I have a class, I may be excused. I have to leave now.
Oh, okay.
So,
Nice seeing you again. Yeah. Thank you so much. Yeah.
Thank you, sir.
Yeah, I think there is a question on the chat. Let us see is it?
Yes, sir. That is question from Pankaj Kumar. Good morning, sir, and thank you for great information presentation. My question is how we select casual cost factor that affecting water quality when we prepare model. Thank you, sir.
That's an excellent question. So that comes, a lot of that information comes from a literature review of the factors based on earlier field work. So for example, if you have noticed the slide where I talked about all of the important processes that influence the bacteria, I talked about sunlight, solar radiation as an important factor. I talked about temperature as an important factor. I also talked about settling and resuspension. And but then I also talked about nutrients, which I did not model. I talked about a few other things. Now, the reason why those are not modeled is because there is their effect on bacterial concentrations is very limited. It's known to be less significant based on literature review of the previous factors that people have identified at similar sites. So I would say if you are developing a model for a given site, earlier work, it probably is not modeling work. It could be just field work. But typically people talk about these are the important processes, and that is very helpful for developing models. And of course, the other way we learn from modeling is we include all of the processes that we think are important. And then once the model is developed and you compare with observed data, you keep some of the terms and you remove the other terms, you will know which of the terms is the most important. So that's another way we can do, but that's a more time-consuming process. So those are the two mechanisms by which we decide which causal factors we should include in our models. Yeah, that's a great question.
Any other questions?
Sir?
Yeah.
Can we use satellite remote sensing as a viable alternate for continuous water quality monitoring?
Yeah, so that's a great question. Satellite monitoring is very helpful for the surface characteristics of these plumes. For example, I showed you those images of those plumes. Those plumes, because remotely sensed data cannot penetrate the water column, other than a few centimeters of the water column, we will not be able to get a complete picture of the water quality within the entire water column, but we can still get some information on the directions of those plumes. And also we can use multispectral data to look at the red, green, blue, and all of the different bands and try to extract some information on the optical characteristics of that water, and we can use some of that. But the fact is, fundamentally, it is somewhat limited by the fact that we cannot get information throughout the water column. Sometimes that is important. So, but it is still useful, especially for testing these models.
Okay, sir.
Okay, sir. If there is any other questions, shall we conclude?
Yes, I think there are no other questions. So, yeah.
Thank you, sir, for that enlightening talk.
Thank you so much.
Now, I would like to invite Dr. Sabida Ennam, Senior Scientist at NATPAC, to deliver the vote of thanks.
Thank you.
Thank you, Jida. So, on behalf of NATPAC, I would like to express our heartfelt thanks to everyone present here today for attending the 23rd session of the TransTech Talk series. It has been an enlightening and insightful session, and we are truly grateful for your active participation. A special thanks to our esteemed speaker, Dr. Phanikumar Mantha, Professor, Michigan State University, for taking time to present his extensive research on coastal water quality and public health in the North American Great Lakes, the science, technology, and policy behind the beach management. Dr. Mantha's expertise and deep understanding of the subject have provided us with valuable insights into the complex relationship between water quality, public health, and environmental management. His presentation today has sparked important thoughts on how science and technology and policy has come together to address this critical issue. We would like to extend our gratitude to the entire team behind the TransTech Talk series, whose efforts and organizing this event has ensured a smooth conduct of this talk. And finally, a big thank you for all the attendees for being part of this event and contributing to the success of today's session. We hope that the knowledge shared here will encourage further discussions and collaborations in the future. Thank you all once again. And also, I would like to thank Dr. Phanikumar Mantha for accepting our invitation and be here in this time. Actually, for him, it will be midnight and presenting this.
Thank you, Savita. Thank you so much for the
Thank
invitation. Really look forward to working with you again. And thanks again, and have happy holidays. I know that this is a holiday season, so I hope all of you have a wonderful holiday season and a happy New Year.
Happy New Year to you, sir. Thank you for coming today. Actually,
thank you so much.
I came to realize the importance of this topic when we discussed about this at the beautiful Alapura
Yes,
beach.
exactly. That is a beautiful beach. Yes, absolutely. And also, this is very much relevant to the topics of blue economy. Especially when we think about how this all has financial, economic implications. That becomes all the more relevant. Yes, thank you.
Thank you, sir, and looking forward for further collaborations also.
Absolutely. Thank you so much.
Thank you.
Yeah.
Thank you very much.
Yeah. Bye.
But I don't know what